All right, the last piece of the chapter that we want to talk about is deflection of beams. Now, deflection of beams is interesting because, beams, we calculate the stress, and we've talked about, hey, maybe beams could have too much bending stress on them and they could fail, or maybe they have too much shear stress on them and they could crack or they could split and that would be a failure. Deflection is a little bit different. Deflection is what they call a serviceability limit state. Okay, so we're more interested in how, in this case, a beam functions relative to deflection. And deflection can be a big deal. I mean, if your beams in your house or your beams in your roof or whatever, if they deflect too much, that can cause serious problems. I mean, it can cause a building to be unusable. All right, so failure does not just mean always falling down. Failure can mean, hey, it's just bending too much, it's deflecting too much, it's not working out the way we had. And think about this even like for a simple doorway. If your header or whatever goes over your doorway, if that deflected too much, your door wouldn't be able to close, would it? So, I mean, you can have things that impede the functioning of, something, and that constitutes failure. Building codes largely look at what they refer to as live load deflection. All right? And the building codes, if you go to where they talk about beams or structures, they a lot of times will talk about an allowable deflection. And a lot of times they'll talk about like live load. So they sort of figure, hey, your dead load, the weight of the beam, the weight of the structure, that's already there. It's going to deflect whatever it deflected because of the dead loads on it. But let's think about how much more it will deflect when the live load is on there. So they will put a limit a lot of times, and you can go to your building code and take a look at this. Go to the building code, look up in the either table of contents or maybe in the back, look up deflection, see what page it's on, and they'll probably give you a table, and they'll have various things, like they'll talk about plastered and unplastered construction, and that's not a big deal. But what I want to point out is a lot of times they say the limit that you're allowed to use is going to be a function or a fraction of span length. So a very common live load deflection limit, and a lot of people call this the allowable live load deflection, would be your span length divided by 360. So for instance, if you did find this in the code and they did say, hey, your allowable deflection is span length divided by 360, what would that mean? Well, we just got done with some examples with a 12-foot long beam, right? Well, 12 feet is 144 inches. So 144 inches divided by 360 is what? 0.4. So, if you saw this in a building code, that's what it would mean. For a 12-foot long beam, that beam should deflect no more than 0.4 inches under its live load. Now, there are some limits for total load. So again, when you read through this material, make sure that sort of if the limit they're giving you is a live load limit, which means just look at the live load, or if it's a total load sort of limit, and then you use the total load on it. But it is a service limit sort of state, serviceability state that we don't want to go over. There's a lot of ways that we can calculate deflection of beams. Some ways are very analytical, get into a lot of deep stuff. All right, what I want to focus on here today is an easier method, but a limited method, and the method that we're going to talk about is just standard deflection formulas. So if you go to your book on page 406, there's like 5 separate cases of these standard deflection formulas. Now I'll stress here that standard formulas basically only apply if you have that exact case. All right? So the first case we see up there says, I would like to calculate the maximum deflection for a beam that's uniformly loaded, a simple beam that's uniformly loaded all the way across its length. And the formula you'll see there that they give you looks like this. Now again, I'll stress that that formula is for maximum deflection at the midspan of the beam, okay, but only for a beam that is a simple span, one simple span, and is uniformly loaded across that entire span. Okay? If you do have this, though, what do you got to worry about? It seems like this should be pretty easily applied. But what do you think the downfall or a potential downfall of this formula is? Units. Units is a big, something you really have to pay attention to. Because let's just say I gave you a beam, and I said, oh, there's 500 pounds per foot on it, and it's 10 feet long, and it's made out of lumber, and that's 1.5 million psi, and it has a moment of inertia of 198 inches to the fourth. And so let's go ahead and start plugging those things in. What's the load? What's the uniform load? Okay, it says 500. Okay, sorry about that. 500 pounds per foot. What's the span length? 10 feet. 384. The modulus of elasticity is 1.5 times 10 to the 6 psi. That's 1.05 million. And the moment of inertia is 198 inches to the fourth. Okay? Now take a quick look at that. What's your problems? Yeah, units that aren't matching up. What do you think deflection should come out to be? I mean, what unit would make sense? Units of deflection. How much something deflects? Inches. Or feet, but I mean, you're not going to deflect by, well, small beams aren't going to deflect by feet. They're going to deflect by fractions of inches. Okay? So, if that's the case, I mean, my pounds is okay because I have pounds down here, right? But this feet, it's not so good. So what do you think really we should do with the load? Multiply by 12. Why would you be multiplying by 12? There is 12 inches in a foot. Yeah, but the feet's in the bottom. So you divide by 12. So 500 divided by 12 gives you what? So this is pounds per inch. What do you think? What about the 10 feet span length? What about that? You would multiply that by 12. Let's put that into inches. Notice that 120 inches is then raised to the fourth power. Okay? Divided by 384, 1.5 million psi. Again, pounds per square inch. That's good. Pounds is okay. And then 198 inches to the fourth inches is okay. Look what's going to happen here. Up top, I got pounds divided by inches times, this would be inches to the fourth. Down on the bottom, I got pounds divided by square inches multiplied by inches to the fourth. So again, Here are the pounds, top and bottom go away. The inches squared on the bottom makes that inches squared right there. The inches on the bottom here makes this inches cubed there. So I end up with inches cubed divided by inches squared. What do I end up with? Inches. Okay? Pay attention to your units on all these things because that'll be problematic.